Hello everyone. This is the first video in a three-part miniseries on the common base transistor circuit. First, we'll provide an overview of the common base circuit, its uses and overall properties. Then we'll dive into a lot of algebra to derive the small signal gain, input impedance, and output impedance, along with approximated versions of these three parameters. And finally, we'll have a brief discussion of the results and calculate the current gain of the circuit to show that it has good properties for current buffering. In Part 2, we'll discuss the Miller effect, which is a generally undesirable aspect of amplifier circuits, and how we can use the common base to mitigate the Miller effect in common emitter circuits using a two-transistor amplifier circuit called the cascode amplifier. And in Part 3, we'll do a lab demonstration of the common base by demonstrating a common emitter amplifier, then showing how adding a common base to the circuit to create a cascode amplifier provides some improvements beyond the common emitter alone. The common base circuit is the final fundamental single transistor analog amplifier circuit after the common emitter and the emitter follower. Here we show a simplified diagram of the common base configuration. We have the input voltage on the emitter, a ground on the base, and the collector connected through a resistor to a DC voltage rail. Output voltage is taken at the collector, as in the common emitter. Now, the first time I saw this circuit, I thought it looked pretty weird, backwards or upside down even. This circuit is a little bit different from the other two single transistor circuits and is not nearly as commonly used as the other two circuits are in low-frequency discrete systems. This circuit is much more often used in integrated circuits and high-frequency circuits. So, what does it do? As we'll show later, the voltage gain is very similar to that of a common emitter and has about the same output impedance. However, the input impedance, instead of being rather high, is instead rather low. Sounds wonderfully useless, doesn't it? Well, it's not intended to be used as a voltage amplifier in most applications. It has two main uses. First, it can be used as a current buffer, and second, it is used to improve isolation between the input and output of common emitter circuits and other similar circuits that suffer from something called the Miller effect. The Miller effect and use cases for the common base circuit will be discussed in the next episode of this mini-series. In this first episode, we're going to confine ourselves to the intrinsic properties of the common base, specifically the gain, input impedance, and output impedance. So looking at the schematic here, just like any other transistor circuit, the common base requires a biasing current and biasing voltages, though it appears at first glance like it's a lot harder to bias due to the input voltage appearing to have to sink the biasing collector current. This makes the biasing more difficult for a simple voltage amplifier in isolation. However, we're going to skip the biasing circuitry discussion for now, as it can get a little ugly when setting it up in a straight voltage amplifier configuration like the previous transistor circuits. In practice, most applications make use of the existing biasing currents from other transistors connected to the common base to significantly simplify the biasing situation. We will, however, add two more resistors to this circuit to make it more realistic and thus make our derivation more useful. I've added a source resistance on the input voltage, as a zero source resistance is the ideal, and rarely are we blessed with an ideal circuit. The other resistance added is a resistance on the base to ground. Now you might wonder what the point of the resistor on the base is, as a simple piece of copper wire from the base to ground can be easily made to be extremely low resistance, much lower than an ohm. However, the resistor on the base is really there to represent resistance within the transistor base's semiconductor material and contacts, as these resistances within the transistor cannot be made nearly as conductive as a metal wire. Now, as I've done with previous transistor amplifiers, the next part is circuit analysis and math to derive the gain, input impedance, and output impedance, along with several useful approximations and changes. This one is very long and contains many walls of algebra, and so if you want to skip some or all of the walls of algebra, refer to the chapters, which will indicate the points at which I discuss the results of the various derivations. So now let's convert this to the small signal model. Since neither the collector nor the emitter are grounded, we cannot easily combine RO with any other resistance, so we must deal with RO in its awkward position as is. My first thought when looking at this circuit was, how do I begin? We need to get V out in terms of V in, presumably by way of calculating VBE. It's a bit daunting. I found the best way to deal with circuits that are difficult to solve is to try to find a voltage or current that we can pretend is static and solve based around that. Then substitute in the real expression for that voltage after the fact. So, what would make this circuit easier to solve? Well, if I knew what the emitter voltage VE was, it would be trivial to get VBE. So let's assume we know VE and solve for V out in terms of VE. Let's label the remaining currents in the system. And now we begin by noting that since VE is known, we don't need to know IC to calculate IB, since it's just Ohm's law with the two resistors from ground to VE. So IB is equal to negative VE over RB plus R pi. It's negative because of the direction IB is flowing, which is the opposite direction that a current would flow through those resistors if VE were a positive voltage to ground. Now that we have IB, we can calculate VBE equal to IB times R pi, and substituting in the expression we just got for IB, we get this. Thus, IC is equal to this. Next, we write out the expression for the current IRO, which is simply the voltage difference across RO divided by RO. We note that the output voltage we need can be related to the current IC prime and RC with this equation. Finally, we write the expression for IC prime in terms of IC and IRO. And with that, we have all the equations we need to relate V out to VE. We just have to do a bunch of algebra and simplification. So I will write out all the algebra for the process, though as I've mentioned in previous videos, the important pieces to understand are the setup, the results, and the rough path we use to get there. In this instance, it involves this intermediate solution of V out over VE, which is equal to this expression. So this expression really just tells us what the gain of the circuit would be if RS were 0, since that makes Vin and VE the same voltage. Now that we have this expression, we can look for an expression for Vin in terms of VE and other values we know so that we can calculate the true gain, V out over V in. To start with, we write the expression for VE in terms of Vin, In, and Rs. Here, we note that we haven't written the expression for In as we didn't need it before, so using KCL, we see that it's equal to IRO minus IB minus IC. Now recall that we already have expressions for IRO, IB, and IC, so we can just plug them into this expression to get an expression for In terms of VE, V out, and known constants. Once we have this expression for In, we plug it into the expression for VE above, and now we have an equation that just has Vin, VE, and known parameters in it. But we still need to get an expression for VE in terms of just Vin and known parameters, so we have to go through another wall of algebra. As we gather all the VE terms on one side and all the Vin terms on the other, note that there's a V out in there, so we need to use our expression for V out over VE to get that V out in terms of VE, which makes the equations even messier. If you wish to examine each equation step by step, you may pause the video. However, I won't discuss each algebraic manipulation as they do not add much to the discussion and are merely a means to an end. Now we've come to the expression for the gain. Let's take a look at it more closely. It sort of looks like a jumble right now in its current state, but there are a few ways to reformat the variables to expose some possibilities for approximations. First, we recall that R pi is equal to beta over GM. It then follows that GM R pi is equal to beta, so we can replace the R pi with beta over GM, and the instances of GM times R pi with simply beta. Also, I'm rearranging the RO values on the bottom, so it's beta plus 1 times RO. That will make sense in a moment. So we're going to apply approximations in stages. This first set of approximations are approximations that are almost always accurate. First, we look at the top of the equation. We have beta RO, RB, and beta over GM. Recalling the equations for RO, VT, and RM equal to 1 over GM, we note that VCE is always greater than 0 in the forward active region, and that the early voltage, VA, is from tens of volts to hundreds of volts. The thermal voltage is 26 millivolts at room temperature and is directly proportional to absolute temperature in Kelvin, so it doesn't change by orders of magnitude over normal temperature ranges. For example, at negative 55 Celsius, the thermal voltage is about 18.8 millivolts, and at positive 125 Celsius, it's 34.3 millivolts. So almost a factor of 2 difference, but over the wide automotive temperature span. As a result, RO is always much larger than RM, and thus beta RO is much larger than RPi. As a reminder, we take much larger than and much smaller than in circuit analysis when making approximations to mean greater than 10 times the value and less than 1/10 the value, respectively. So a factor of 10 is the magic number we use. This obviously doesn't apply in all situations. However, in small signal analysis, we're already using an approximation, and precision analysis tends to be reserved for more special circumstances that use a combination of test data, high-fidelity simulation data, and negative feedback to make nonlinearities and non-idealities truly negligible. Now, thinking about RC, if RC is actually an active load, it could be on par with RO, and so we can't always rule out them both being about equal. However, even if RC is an active load, beta RO is much larger than RC because beta is much larger than 1, and so we can make this approximation. Finally, RB is usually comprised of an unavoidable resistance within the transistor called the base spreading resistance, as well as contact resistance, and maybe a small amount outside the transistor. There is rarely any reason to increase this value beyond the limitations of the transistor and bias network in the common base. Base spreading resistance is highly variable, but tends to be between a few tens of ohms to a few hundreds of ohms, though can be higher or lower depending upon what transistor you're working with. However, the internal transistor resistance is almost always less than 1 kiloohm, and so, barring unusually low early voltage and extremely high bias current, RO is almost always much greater than RB. Using these approximations, we can remove some terms on the top and bottom due to the dominance of beta times RO, then divide top and bottom by beta RO, and make a few more adjustments to the resulting equation, recalling the definition of the parameter alpha and pulling out a factor of 1 over GM on the bottom there, and we get this equation. Finally, we convert the GM RB over beta to RB over RPi and the 1 over GM to RM, resulting in this equation. This might look like an odd way to format the equation, but it's sort of formatted as a stepping stone to the next set of approximations. This equation may be useful for calculating a slightly more accurate gain than the version we're about to derive. For our next set of approximations, we'll deal with RB and RPi first. If beta is large enough and the bias current IC is not too large, and RB is not too large, then it becomes clear that RPi will be much larger than RB. High beta makes RPi large, but high IC makes it small, so if the bias current becomes too high, this assumption can break down, especially since beta will start to drop as well if the bias current becomes too high. So keep that in mind when making this assumption. Second assumption is really more of a directive. If you can make RO large enough by keeping IC small, choosing a BJT with a large VA, and by choosing RC so that it's much smaller than RO, then you can make the assumption RO is much larger than RC. This clearly breaks down if you try to maximize RC with something like an active load. And finally, we make the common assumption that beta is much larger than 1. This is almost always true, and so alpha can be assumed to be 1. So, this results in those conveniently constructed terms RB over RPi and RC over RO to each become approximately 0. Because since RB is much less than RPi, then it follows that RB over RPi will be much less than 1, and thus 1 plus RB over RPi will be approximately equal to 1. Same logic applies to RC over RO. And of course, since alpha is approximately equal to 1, then 1 over alpha is approximately equal to 1 as well. This results in the approximation of V out over V in equal to RC over RM plus RS. This is a simple result, and so if you can adhere to these approximations, you can use this result with pretty good accuracy. Now, at this point, we split the approximation into two paths. As I said before, the common base is more often used as a current buffer. This means that RS would actually be large instead of small, as current sources generally have somewhat higher impedances than voltage sources. We'll show the relationship with a current source later once we've gone through the voltage gain, input impedance, and output impedance. But right now I'm going to show two separate approximations, one with very low RS and one with very high RS. First we'll start with very low RS, which is the voltage amplifier case. If we assume RS is very small compared with RM, which is actually a pretty tall order, this means for a collector current of 1 milliamp, the source resistance would have to be about 2.6 ohms or less at room temperature. For 10 milliamps, it would imply a source resistance of 260 milliohms or less, so a very low resistance case. Then we can eliminate RS from the equation. Noting that GM is equal to 1 over RM, we can reformat this slightly to get the classic voltage gain equation for the common base. Now this looks almost the same as the common emitter. The only difference is that it is positive instead of negative. This is an interesting point, though as we've mentioned, that because the input is on the emitter, not the base, means that the input impedance is much lower. But if you happen to have a very low source resistance, you can easily estimate the gain with this equation. Now let's look at the large source resistance case. For large source resistance, the denominator of the gain equation in blue above just goes in the other direction, and we get a gain of RC over RS. Not much more to say about this right now, we'll revisit it later in the video. Now that we've derived the gain equation, let's move on to the input impedance derivation. To get input impedance, we must find Vin over In. Since in this setup we're setting our input voltage to the value Vin, so to speak, we can calculate input impedance simply by finding an expression for in terms of Vin and known values. We start by pulling an expression for Ve that I wrote during the gain computation, which is in terms of In, Vin, and Rs. Then we recall the expression for Ve in terms of Vin and known constants, then substitute in this expression for Ve in the first expression, which gives us an equation in terms of known constants, Vin and In. So we just have to algebraically chew through this for a while. Pause if you want to see any specific steps. Until we get this expression, which is unsimplified. Separating out the RS term on the numerator reveals that we can cancel out some of it to simplify a portion of this to just RS. Though more importantly, we can actually zero out RS, because when calculating input impedance, it's not supposed to be part of this equation. We could have done it earlier, but this shows that if you leave it in, it appears as a term in this input impedance expression as just being simply added to the rest of the input impedance, as we would expect. So it's kind of a sanity check that our algebra is correct. Making a few more adjustments, we finally get an input impedance of this. So as with the gain, this is the more accurate expression. However, it is of limited use as there is too much going on here. So we'll continue by making some approximations to help simplify things. The first approximation that is often true is that beta is high enough, RB is low enough, and IC is low enough such that RB over beta plus 1 is much less than alpha over GM. This relies on some restrictions on RB and collector current, especially if beta is not very high, so it only works for some situations. This approximation allows us to render part of the numerator negligible. We established before that beta RO is almost always much greater than RC, and beta is almost always large enough to justify the relation that beta plus 1 times RO is much greater than RB plus RC. This approximation allows us to zero out a term on the denominator. A third approximation is one of the approximations from the gain derivation that RO is always much greater than RM, which is approximately equal to RE, and so RO is much greater than RE. So, using these three approximations, we can see that each will eliminate a portion of either the numerator or denominator, as it will indicate that the portion is negligible compared to the other terms being added to it. So, applying these approximations and canceling out those three terms results in a smaller equation, which as before, we reformat to prepare for the next set of approximations. Let's pause here for a moment. Here we see that the input impedance appears to be alpha over Gm divided by a resistive divider consisting of Ro and Rc. So if you can't make this final approximation, this equation is pretty simple already and may be more useful to you. The final approximation to get the classic input impedance for a common base is assuming, or rather ensuring, that Ro is much greater than Rc. Again, this does not work out if Rc is from an active load or something similar. However, if you do happen to have Rc much less than Ro, then the Rc over Ro term goes to 0, and Zin simplifies to alpha over Gm, also known as little re. So with these approximations, we get a very straightforward input impedance. This is also the typical approximation of the impedance looking into the emitter, regardless of the kind of circuit used, though in other circuits the impedance at the base can often change that significantly. As we discussed at the beginning, the input impedance is quite small. Even with a fairly small collector current of 100 microamps, Re is still about 260 ohms. At 10 milliamps, it's only 2.6 ohms. So it's a pretty small value over most reasonable collector current ranges, especially the higher ranges. So not an ideal input impedance for a voltage amplifier. Finally, we move on to the output impedance calculation of the common base. For the output impedance, we can actually do a little trick to simplify the math since we have the gain already. Here's the gain from our previous derivation. In this case, there is no load current, and so the output current is 0. Now what if we added a load resistance from Vout to ground? Not a load current, but a load resistance. We'll call it RL. So we can really think of this as two different situations in the circuit, one with RL not present, and another with RL present. As the presence of RL affects the gain of the circuit, we need to write two different gain equations. Fortunately, we can easily see that since RL goes to ground and it's on the output voltage node, we can simply put it in parallel with RC and replace all instances of RC with RC parallel RL in order to get the modified gain. So now we write the two gain equations, one with no load resistance and one with a load resistance of value RL. I've called them AV1 and AV2 respectively. You'll notice that I've written them as Vout1 over Vin and Vout2 over Vin. Vin is the same for both because I have set it that way. This is a key point, as we'll see in a moment, for calculating Zout. So now that we have these two expressions, we know these are the appropriate gains for each situation. However, because this is a linear system, there is a separate way for us to calculate the gain when we put down a load resistance RL. First, we note that this circuit can be modeled as a perfect amplifier with Vin on the input and gain of AV1. This perfect amplifier, represented by the triangle, also has 0 output impedance. We then add a series impedance placed after the output of this perfect amplifier labeled Zout to model the currently unknown output impedance we're trying to derive. Note that Rs does not appear in this diagram. That is because the effect of Rs on gain from the Vin perspective is folded into the gain of the perfect amplifier. This is valid because our circuit assumes a Vin perfect voltage source going into Rs. Also, we don't have to think about the input impedance of this amplifier because it's being driven by a perfect voltage source Vin, and so the input impedance doesn't matter. The effect of Rs and the input impedance on the output voltage is already handled by AV1. So, due to linearity, we can make these assumptions. We know that there is an output impedance Zout, and we know in the case with no load resistor that there's no output current and thus no voltage drop across Zout. Thus, with no RL, both the voltage at V1 and the voltage at V2 are equal, and equal to Vout1, as our perfect amplifier has a gain of AV1. If the load is equal to RL, the voltage at V1 will not change, and is still Vout1 because the amplifier is still a perfectly 0 output impedance amplifier. However, V2 is now equal to Vout1 times this resistive divider comprised of Zout and RL. Now here's the key point. V2 is also equal to Vin times AV2, since AV2 specifically incorporates RL into the gain equation, and thus V2 also equals V out 2. And now we have enough to solve for Z out using equations we already have. So first we combine these two equations together, so we have V out 2 equal to V out 1 times the divider. Then we divide both sides by V in, which was the key I mentioned earlier when I said that V in was the same for both situations. We get this expression to contain the gains, which are known values, along with Z out and RL. We still have RL, which is technically a variable, and thus an unknown, but we'll hopefully cancel it out as we go along. Then doing some algebra to rearrange terms, we get this expression for Z out, which is only known values and RL. Because the system is linear, we do not expect the output impedance to depend upon the value of RL. We used RL only as a dummy variable, and we will see that it cancels out once we perform the necessary simplifications. So now comes another wall of algebra. Pause if you want to see specific steps, but as before, I will move through the algebraic manipulations without discussing them. So here we finally see that all the terms containing RL have been cancelled out. Now we just need to do another wall of algebra to simplify this. I'm going to take a moment to mention why I'm doing all this algebra. The truth is that you don't need to do all of this algebra in order to solve your equations because we have algebraic solvers for this kind of thing. The important thing is knowing how to get to a point where it's easy to input into an algebraic solver. There's some degree of difficulty when it comes to creating a simplified solution at the end of the line that looks useful, and so to some degree these walls of algebra make sense in that regard. But for the most part, once you get to the point where I'm saying there's a wall of algebra, you could just take the equations and put them into a solver and get the end result. So that's the recommended strategy for most situations. When you're trying to do analysis for a circuit, you need to have an analysis done. Maybe if you're trying to learn the way things kind of go, maybe you do some more algebra, but a lot of this algebra is not very illuminating, and so I really just do it for completeness of seeing, how much algebra is done. Now, this particular method I said I can make a simplified method by using the definitions of Z out and using the linearity principle. And when I said simplified, I didn't mean make the algebra more simple. In fact, I probably made the algebra more complicated. But I made the process of getting to the point where we can just dump it into a solver more simple, because it was pretty straightforward. We used some equations we already had, and we were able to get it into a situation pretty quickly and pretty easily where we could just input the equations into a solver. So here we have a somewhat concise equation which shows RC in parallel with a few other things, which is what we expect. Bringing back the small signal diagram, and recognizing that one of the terms can be rewritten as a parallel, we can finally write the equation for Z out in terms of known values. So as with the gain and input impedance, this more accurate expression for Z out is of limited use, though it does allow you to see how things like RB, RO, and beta affect the result, and you can use it to see if your assumptions hold up with the more approximate versions. Let's see how we can reduce this down. As with the gain before, we're going to split this into two sets of approximations. For the first set, we'll look at the very low source resistance case. Note that this is assuming a resistance of less than Rm, as we used in one of the gain approximations. We start by rewriting R pi as beta Rm and dividing the top and bottom of this one term by beta Rs. We see that beta cancels out here in one term and Rs cancels out in the other term. So next we look at the denominator and see what we can change. And what we see is that since Rm is much greater than Rs, that means that Rm over Rs is much greater than 1. and all we need to know about the other two terms is that they're positive, which is guaranteed since beta is always positive, and so long as you use positive resistances, and don't use something weird and arcane like a tunnel diode. Under these conditions, we can conclude that this whole coefficient on RO is much less than 1, because the denominator is much greater than 1. And since it's added to 1, we can therefore conclude that this big portion plus 1 is approximately equal to 1, which just reduces down to RO, producing this expression. Now we can further reduce this down by recalling that since R pi is beta times Rm, that Rs being much less than Rm implies that Rs is also much less than R pi. This fact, in conjunction with Rb being positive, means we can eliminate the Rb plus R pi portion of this term, resulting in this expression. Finally, since, as we've established previously, that Ro is much greater than Rm, and since Rs is much less than Rm, that implies that Ro is much greater than Rs, and so that implies that Ro plus Rs is approximately equal to Ro, finally leading to this expression, which is much simpler and familiar as it is the same as the output impedance of the common emitter. Now we look at the second approximation, that of Rs being large, much greater than Rm. We also assume Rb is much less than R pi, and Ro is much greater than Rm, which has been established previously is always true. So looking back at our equation here, we can immediately get rid of these, Rb's, cleaning things up a bit. Let's take a closer look at these two terms of the equation. We'll use a method of evaluating what simplifications can be made by putting a question mark between these two terms. This allows us to treat them like an inequality without knowing what it is yet. There is an important caveat. Since we're dealing with the much greater than and much less than signs, we can only use multiplication and division on both sides. We cannot use addition or subtraction. This could break our much greater less than relation. For example, 10 is much greater than 0.1, but if we added 1000 to both sides, 1010 is not much greater than 1000.1. So to start with, let's expand the right side of the inequality and multiply both sides by Rs plus R pi, which will produce this inequality. So now we divide both sides by Rs times beta, and when we substitute in beta times Rm for R pi, we get this expression. So here, things actually get quite simple. We have a 1 there, and we know that beta, Rm, and Rs are all positive. And so the left-hand side of the equation is always greater than Ro. And from the assumptions in blue above, we know that Ro is much greater than Rm. Thus, this left-hand side is much greater than the right-hand side, Rm. And by extension, these three equations are much greater than as well. This means that the Rs beta over Rs plus R pi plus 1 times Ro term dominates, and this approximation can be made. Continuing along, we combine the Rs beta over Rs plus R pi with the plus 1 term and make some substitutions, resulting in this expression in terms of Rs, R pi, and Rm. Rearranging terms and substituting in alpha, we get this expression. We can now note that both alpha is always less than 1, and that Rs is much greater than Rm, implying that Rs is also much greater than alpha Rm, which allows us to make a final approximation, resulting in this approximate expression for Z out. Okay, now that we've performed all these long algebraic derivations, let's examine some of the results and see what insights we can draw for them. So here we have the unapproximated expressions for gain, input impedance, and output impedance. As I've mentioned before, these expressions may be useful when trying to get more precise answers, under conditions where common approximations cannot be made, and to see what the limitations are, or as a starting point for making a new set of approximations for a given circuit. But written as they are currently, it is difficult to intuit what is going on. So we'll move to looking at the more approximate versions. First, we'll look at the gain, input impedance, and output impedance when we make approximations for a low source impedance. We'll call this low source impedance voltage source input approximation. Here are the set of approximations we must adhere to in order for these approximate solutions to be valid. And here are the approximate gain, Z in, and Z out. We can slightly further approximate the gain to GMRC because we had to assume RS was much less than RM to get the output impedance approximation. And the output impedance can be approximated to RC because, as we made the approximation that RC is much less than RO for both gain and input impedance. So the fully approximated gain, input impedance, and output impedance for this setup is just GMRC, RE, and RC, respectively. Let's pause for a second and think on this. So this common base has the same gain as the common emitter, except positive. Same output impedance as the common emitter, but much lower input impedance, a factor of beta plus 1 lower, which is quite low. So it does appear to be not very useful as a voltage amplifier, except for perhaps special applications where the extremely low source resistance is not difficult to manage. One point in this circuit's favor is that there's a lot less capacitive coupling between the input and the output. This is because there are two PN junctions between the input side, the emitter, and the output side, the collector, rather than just one. And there's also a ground node connected to the base between the two, which will tend to make the input side and output side have a lot more capacitance to ground than to each other. This reduced capacitive coupling feature is important for the Miller effect, which we will discuss in the next video. However, the reduced coupling still does not deal with the much greater problem of the tiny input impedance. So we've determined that a small input impedance is bad for a voltage source, especially one with a reasonable source resistance. But what about for a current source? It turns out that for a current source input, a low input impedance is actually exactly what you want. So let's examine what happens when we make some assumptions that are geared toward a current source on the input. Current sources have high source impedance. In the ideal case, this source impedance is infinite. However, as with voltage sources from sensors and other real devices, current sources similarly do not have ideal properties. And so their source impedances are high, but we don't want to have to rely on them being too high. Fortunately, the first approximation we need to make is that the source impedance is much greater than Rm, and since Rm is generally pretty small, this approximation does not seem to be much of a stretch for most real-world current sources. So using the approximations for high source impedance we derived previously, we see that the gain is now equal to RC over RS, and the output impedance has turned into this more complicated expression. However, we can show that this expression, RS times beta plus 1, over RS plus R pi, with our assumption set, can be shown to be greater than 1. This fact, along with our assumption that RO is much greater than RC, means we can approximate this to be RC, as before. Now, we know what the voltage gain is under these circumstances, but let's find one more parameter, the current gain, which, as we'll see in the next video, is very useful for when we combine the common base with the common emitter. Current gain is defined as I out over I in. Fortunately, due to many of our assumptions, calculating this is quite straightforward. Since RS is assumed to be much larger than RE, that means that the voltage at the emitter, VE, is approximately equal to I in times the input impedance, RE. Which, rearranging a few terms, comes to alpha In over GM. Now, VE wasn't in any of our equations. However, the gain from VE to V out, meaning V out over VE, is exactly the same as the gain from V in to V out under the condition of RS equal to 0. So we revert our gain equation back to the version where RS is much less than Rm, and indeed much less than everything else. And we get our expression of GMRC again. We'll refer to this expression of V out over VE as AV prime. If we then substitute in the value for VE we calculated, then rearrange it, we get an equation that has V out and I in it. We just need to find an expression for V out in terms of I out. Well, one more important point about current gain is that similar to making the source resistance very high on the input side, we have to short circuit the output to ground to get the short circuit output current. So this necessarily modifies our gain equation by effectively adding RL back in parallel with RC. If we then assume that we make RL very small, or approach 0, then we can conclude that all the current flows through RL, and that RC parallel RL is approximately equal to RL. And since all the current flows through RL, we can rewrite an expression for I out in terms of V out, just with Ohm's law. I out equals V out over RL. Rearranging this to get an expression for V out, we can then substitute in this expression for V out in the above expression, getting an equation with I out, I in, and known constants. It also has RL in it, which isn't quite a known constant, but as before, RL will cancel out. Simplifying this, we calculate that the current gain I out over I in is equal to alpha, which is approximately equal to 1. This makes intuitive sense as we've effectively made approximations that largely eliminate RO from the circuit, which means that the current into the emitter from I in will flow out of the base and collector. And since the base and collector currents have a relationship of 1 to beta, then it follows that a slightly lower current, by a factor of alpha, will end up flowing out of the collector and out into the load. So the common base produces a current gain of 1, similar to the voltage gain of 1 produced by the emitter follower. This means that, like the emitter follower, the common base can serve as a sort of buffer, except for current instead of voltage. For buffering, I like to think about whatever is least stressful for the circuit as a good input for a buffer. Another way of thinking about it is what produces the least power dissipated from an ideal source. For an ideal voltage source, the least stressful circuit to connect to it is a high impedance circuit, an open circuit. This dissipates the least amount of power as zero current would be drawn, in contrast to a short circuit which would draw infinite current and thus dissipate infinite power. For an ideal current source, the least stressful input to connect to it is a low impedance circuit, a short circuit. This causes the voltage to be zero and therefore dissipates the least amount of power, in contrast to an open circuit which would cause the current source to create an infinite voltage and thus dissipate infinite power. So looking back at our input impedance, we see it's little re, which is a pretty small resistance, good for an input to an ideal current source. Now, the ideal output impedance of a voltage source buffer is a low impedance output. This allows the buffered voltage output to be unaffected by changing current draws and maintain a copy of its input voltage on the output. Conversely, the ideal output impedance of a current source buffer would be something that would maintain a good copy of its input current regardless of what impedance is on the output. So a high output impedance is the ideal impedance of a current source buffer, as that would maintain an output current close to the input current regardless of the impedance on the output it is connected to. Looking at our output impedance, this shows the version without RL. The output impedance can be increased by increasing RC to some degree, without significantly affecting the input impedance. However, as RC increases, multiple approximations will break down as a greater fraction of the output current flows through RO, and we can no longer neglect it in the equations. So long as the load impedance is not too high, this should work well as a current buffer. That concludes this video. In the next video of this mini-series, we will be discussing the Miller effect, which is a generally undesirable effect for high-frequency circuits, as well as a new circuit called the cascode, which utilizes the common base to mitigate the Miller effect in some circuits. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have any comments or questions, leave a comment. See you next time.